Okay, I'll show you. I have it connected, so I'll show you after drawing. So it's like a copper plates, thick copper plates. Why do you need thick copper plates? Any idea? Conduction will be? Good, right? There is no resistance at all. Bigger the copper thickness, right? So area bigger means resistance will be very, very low. So instead of using a wire, use thick plates. So this is resistance box, right? This is unknown resistance S. This will be connected across a wire 1 meter. No. Nichrome, Constantine, manganese. We talk about that. Resistance wire. So this is your resistance wire. By the way, we are talking about meter bridge. So if I connect it over here, I can connect it like a cell like this. So from here center, we will connect it to a galvanometer. Then there will be a jockey J. Jockey in the sense it is mobile key or mobile contact point. These things you can call it as copper strips. So just try to compare this and this, right? So listen here. So I have a battery here, right? You have a battery there. And look at this. In place of P, what do you have? You have the resistance box. Okay. In place of Q, what do you have? S. Right. In place of R and S, what do you have? There is a galvanometer in between here, right? And in place of R and S, what do you have? A and B is the resistance wire. So basically you have this resistance and this resistance, right? So because of the jockey J, right, it is kind of split into two resistances. This is a separate resistance, this is a separate resistance. 0, which means there is no current flow, right? So can everyone see this? So this is the copper strips I'm talking about, right? Because we can assume that the resistance here is exactly 0. So there is no resistance at all, right? So you have two gaps here. That's the gaps shown there. So I'm going to connect this resistance box over here, and then the unknown resistance is on the other direction, other side, right? Maybe it's just moved here, that doesn't matter. So on the scale, can you see a wire here? Maybe from there, I don't know if everyone can see it. You see it, right? So this is your resistance wire, right? So in the resistance wire between A and B, I am going to connect the battery. So which means your battery eliminator. So I need to bring this closer. So plus is connected over here, minus is connected over the B point, okay? And then this is my resistance box. Right now I have 100 ohms taken out, which means this will offer 100 ohms, right? So I need to have some connecting wires again. I think you will get some practicals also in this, okay? So make sure you are understanding this properly. So you have a practicals. So this is your terminal points, right? So you have to connect it to this point over here. So far what I have done is I have connected the battery to the AB, right? I have connected the resistance box across these two junctions, right? Two gap here. And then I already have some unknown resistance here, right? You already know color coding, right? So based on the color coding also you can check the resistance. But in this experiment we are going to accurately calculate the resistance. Okay. From the center connection, right? From this center connection, it goes to a galvanometer, right? So it goes into the galvanometer and then comes out of a. This is what I am talking about. So it's a movable contact. So meaning I can contact like this, right? So that's what is a jockey. So you can keep moving it. But the only problem here is you should not just scratch it, right? So if you scratch it, you will be damaging the area of the wire, which means if you change the area, this experiment will not work. So even when you are doing some practicals, right, make sure you make a note of this. So if you want to move it, just take it out and move it. So that's the proper way of moving. So right now I have not switched on the system. So before going into this experiment, right, let me show you what's happening at the ends here. So plus is connected over here, so I'm going to put my lead here. So look at this. So suppose if I put my lead here, what is the voltage? Negative. Why negative? This is. Is it positive? I think it should be positive. Negative. Why do you think you are getting a negative? Now it's coming positive. Maybe the voltage is not sufficient, so let me try increasing it. Okay, so look at this. Can't see it. So if I put the voltage across AB, right? So I'm touching the leads on A and B. So what is the voltage? 0.9. It's so low. What happened? Okay, please hit it. About to finish. What is the voltage? 1.76, right? So between A and B, the voltage is 1.76. So carefully look at this, what's happening now. So if I put my, so plus is coming here, so I'm just point. Now? 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 1.5. 0.0. I think it should be slowly increasing. What is the voltage now? 0.04. 0.04. So 1.30. Maybe the contact I'm making is not 1.3, right? So if I move it further, 1.5. So if I go further, 1. Okay, so something wrong at this point. 1.6, right? I saw some 1.6. I think some contact is having some issue. So what is that I'm trying to show you here? As the resistance increases, voltage also increases, right? So it's going through the resistance wire, right? So we talked about this. As the resistance increases, the voltage keeps increasing, right? When we are talking about what is voltage at a point and voltage difference between 2 points. Remember that? So that's why I'm just trying to show you that. Okay. So here it was 0.1, here it is 0.2, 0.3, 0.5, 1.5, 1.6, 1.7, 0.8. So it keeps on increasing. So suppose if I increase the voltage, again you will see it will be increasing slowly. 0.2, 0.5, 1.03, 1.4. Are you able to understand? So as resistance is increasing, right? Because of the resistance wire, length increases means resistance is increasing. Okay, so that's just an additional thing. So we have to finish this quickly, so it's already time. So I have unknown resistance here. So what I'm going to do here is, see if you can see this. So if I put my jockey somewhere here, you see the deflection is on this side, right? So if I put it on this side, you see the deflection is on this side. So somewhere here I'm going to find a point where there is no deflection at all. So you see the deflection is less here, somewhere close to 42. 44 is more, so that means I'm going to go closer to 41. So 41 I don't see any deflection. 40 it's deflecting on the other side. 42 it's deflecting on this side. So 41. So I told you, no, don't scratch it, right? So if you do that, you will be changing the area and all your results will be gone. Okay, so don't do that. So just gently just take this out, press it slightly. So this is the way you have to do this, right? So coming back to this 41. So around 41 I see there is no deflection, right? You following that? Janak, what is that? Why are you not listening here? Not interested? So 41 I don't see any deflection. So that means that is my, so I'm going to say at this point it is going to be 41. So on this side it is 41, yeah. So here it is 41, and this is a meter bridge. So if this is 41 centimeters, what can you say about this one? Is it 49? 59, right? So this side it's going to be 100 minus, yeah. Okay, let me quickly finish this theory. So I'm going to say, based on this concept here, this by this, right? So I'm going to say, let's call this as R resistance, RS, and this is, I'm going to call it as P and Q. So the resistance here is P, the resistance here is Q, right? So I'm going to say, based on that Wheatstone principle, what can you say? This by this is equal to this by this when there is no current flow through the galvanometer, right? So that's what we achieved now. So I can say R by P is equal to S by Q. R is the resistance box, which is a known resistance, right? So let me finish the theory and then I will show you the numbers there. P is, what is P? The resistance at AJ. So R is equal to rho L by A. So I can say rho L1 by A. I'm going to call this as L1. If this is L1, what is this? 100 minus L1. Right? So this is S by rho L2. So instead of L2, I'm going to write it as 100 minus L1 by A. What can you say about the resistivity of this wire? Is it same at AJ and JB or is it different? It's the same wire, so resistivity will be same. What can you say about the area, cross section? Same. So that means rho cancels, AA cancels. Do you agree? Because it's the same wire. So make a note, same wire or resistance wire. So that means I can say RL1 is equal to S by 100 minus L1. So S is my unknown resistance. So S is equal to 100 minus L1 divided by L1 into R. So that's what we are having. Very simple. So nothing very difficult here. So these are all areas where you can score very well. Yes, if you understood this. So now let's do this quickly. So 100 minus L1 is 59. 59 divided by 41 into known resistance. I said I had taken 100 ohms. So that means it is 100 here. So what is the value? 1 point something. What is that you are getting? 59 by 41, 1.4 something. 1.4. 1.4 into 100 will give me 140 ohms. So So that means unknown resistance which I connected here must be close to 140 ohms. So if I want to double check it, I can go back to the resistance. So maybe in the circuit it doesn't work very well. So I'm getting 146 something, right? So if you calculate it accurately, we'll get 146. 143, okay. So that means, as I said, sometimes this will have some errors. So 143 would be the accurate